All right, we're going to look at a simple, fun application of calculus involving the derivative, and that's called linear approximations. So the idea in this video is we can take a curve and approximating use the simplest type of function we can, which is a straight line. So let's take a look at a picture of what this might look like. Suppose, let's set up our axes here. Suppose that we have a curve, some function that looks like this. Let's call that y equals f of x. And we want to approximate this curve with a straight line. Now, we can't do that well everywhere all at once. So what we can do is if we pick some x value, let's call it a. If we pick some x value a and locate the point on the curve, we can approximate the curve close to that point. So the way we do that is we use the tangent line because it behaves very similar to the curve near that point. If I zoom in here, I'll see if I can do that very well. Yeah, that's pretty good. So if I zoom in near that point, what I'm saying is, well, the curve and the line don't differ by much when I'm near this a value. And so when I'm hugging near that a value, then the tangent line is a decent approximation for the curve. The outputs of the tangent line are close to the outputs of the curve. Now, close to is a relative term, right? So what I mean by that is in applications of mathematics, many times finding exact answers is very hard. Solving math problems in general is very hard. And our math classes give us a false sense that we can always find an answer. So we can find answers to problems for which we can find answers. Problems for which people have discovered, mathematicians have discovered ways to solve them. But there are other techniques that allow us to approximate things to be as precise as we'd like them to be. For example, when you type something like the sine of 29 degrees into your calculator, how does it calculate the value? Well, your calculator can only show so many digits of that answer anyway. So what it's doing is it's approximating that answer using some algorithm that it knows, okay? So here, we're doing the same kind of thing. We're going to approximate the curve with a straight line, and that could be useful for different things, as we'll see. Now, what is the benefit of this? Well, one benefit is calculating the outputs on a curve might be calculation intensive. Okay, so this function f of x could be a lot of computational problems for us. Logs, trig functions, exponential functions, fractions, all sorts of things, roots, whatever it may be. But the equation of a line is very simple. So this line, this line that's approximating the curve, we typically might name something like L of x for linear function. And the equation of a line is always simple. It's just mx plus b. So we just need the slope and the b value, and we can get the equation of this line. So we can approximate the outputs of the curve, the f of x function, by plugging those x values into the very simple linear function. Very simple calculations. Let's get started with examples. So the first example, let's do this. Part A, we'll break this into multiple parts. Let's find the linear approximation. Find the linear approximation for the function f of x equals, let's do the cube root of x, okay? Now, the cube root of x is a curve, right? And when we say a linear approximation, we have to pick a part of that curve to approximate. So what we would say maybe is find the linear approximation for this curve at x equals 27. And so usually you want to do this near a nice input for the function. And in this case, 27 is a decent input for a cube root because we can easily calculate the output of the cube root function for the input of 27. Okay, so here we go. To give you the idea of what's happening, let's consider the graph, a basic picture of what this is showing us. Okay. So we're not just lost on the technique, but we understand what's happening. So the cube root function, in the first quadrant, it looks similar to a square root function, maybe something like that. And whenever x is 27, we land at this point up here, right? This is the y equals cube root of x function, or f of x equals cube root of x function. So the y value here is the y value 3, because the cube root of 27 is 3. And I meant to change colors here. Let me do that real quick. I always like to write my original problem in one color and all of my work in a different color, so I can tell where the question ends and my work begins. All right, so what we're looking for here is the tangent line to this curve at this point. So I'll try to draw it basically, something like this. So there's our tangent line at this point, okay? So what we're trying to do is find this L of x formula, okay? So what we need to find L of x is our slope. Now the cool thing about the slope of this tangent line is we've developed a calculus principle to help us find that. So when we want the slope of the tangent line, it's literally defined to be the derivative of this cube root function at the x value of 27. So the slope of our tangent line is f prime, right? The derivative of the curve, that's this tangent line slope, evaluated at the x value of 27. And we know that upon looking at this cube root of x function, f prime of x, well, this is, if we rewrite it, this is f of x equals x to the 1/3 power, right? So f prime of x, using the power rule, is 1/3 times x to the negative 2/3. So now, if I want to know the slope of the tangent line, I just plug this x value into my derivative formula to calculate that slope. So I need 1/3 times 27 to the negative 2/3 power. Okay, so I've got 1/3, and the negative 2/3 power means take the cube root of 27, which is 3, and then raise that to the negative 2 power, because that's the piece that's left after we've done the cube root. So we've got 1/3 times 3 to the negative 2nd power is 1/9, and 1/3 times 1/9 is 1/27. So the slope of our tangent line, right, or the slope of this linear approximation, is 1/27. Now, we know the slope, now we have to find our b. So the easiest way to do that is to understand that this point in red, is a point on the curve and it's also on the line. Okay, so this point is the point where x is 27 and y is 3. So what we can do now is we can use these x and y values along with our slope to find the equation of the line in point slope form. So what we have is y minus the y value of 3 equals our slope, 1/27, times x minus the x value of 27. Okay? So now, this is the equation of our L of x function, understanding that the variable y here represents L of x. So all we need to do now is put it into the mx plus b format. So we can distribute our 1/27 and add our 3. So we get 1/27 x. We get minus 1, but plus our 3 is plus 2. So the linear approximation, L of x, is 1/27 times your input x plus 2. And that is what this question was asking us for. It's asking us for the equation of this tangent line, which we've done before. One of the first things we did with derivatives in calculus was find the equation of a tangent line, and there we go. But now, what we need to understand is that the outputs of this function will closely match, so L of x, the outputs of that function, will be approximately the same as the f of x curve. Okay, so that's important. The linear function is the outputs of the linear function are approximately equal to the outputs of the curved function f of x near x equals 27. And that's it, just close to that x value. When you start to get further from 27, right, when you start to get into x values over here, you can see this gap between the line and the curve starts to grow. And the further you get from your x value, typically the bigger that gap is going to be. But we're guaranteed that if we're near this x value, then our linear approximation is an approximation of the curve. And so what that means is the cube root of x function, which is f of x, I can calculate the cube root of an x value by approximately by plugging those x values into the L of x formula, which is much simpler to calculate. Okay? So this is our linear approximation near x equals 27, and this is what it means. This is the meaning of it. Okay? The meaning is that the output of the linear is approximately equal to the output of the curve. Sorry to go on and on about that. I want to make sure it's perfectly clear. So part B now, I can use this approximation as long as I use x values close to 27. So now what I want to do is find an approximation. Find an approximation for, let's say, the cube root of 28 using part A. Okay? So in part A, we learned that the cube root of an x value is approximately equal to 1/27 times that x value plus 2, as long as the x value is near x equals 27. So for our purposes, we will say that 28 is near x equals 27. And so using this approximation, we can say, all right, let's plug in 28 for x, which on the left side gives us the cube root of 28. That is approximately equal to 1/27 times 28 plus 2. And we don't need a calculator for this. So what we get is 28/27 plus 2, which is, well, 28/27 is 1 and 1/27 plus 2. And so we get 3 and 1/27. So this is approximately the cube root of 28, and all we did was plug 28 into a linear function. Without this, all we could say is that, well, the cube root of 28 is a little bit bigger than 3. Okay? So there we go. And what we could do now is, using a calculator, we could compare. So we could use a calculator to find the error, right? And even our calculator is going to approximate. So what I could do is I could type in the cube root of 28, which is the exact value. Actually, let's take our approximate value first. So 3 and 1/27. I could subtract the cube root of 28. The reason I went in that order is because if I have an over approximation, I want this to be a positive number. So I'm going to take my approximation minus the real value and see what the calculator gives me here. So I have, let's see here, 3 and 1/27 minus the cube root of 28. And the error here, even though 28 is an entire unit away from 27, the error here seems rather small. It looks like it's about 0.00480651614. Okay, as long as I didn't transpose any numbers. So you can see that this simple approximation we got is actually rather close to the cube root of 28, and it wasn't that difficult to do. All right, so now let's try another example where we go right for an approximation. So in this example, let's use the linear approximation. Let's use the linear approximation for the sine of x function near x equals 0. Let's move this down here. Near x equals 0 to approximate the sine of 0.1. Okay? Now, the sine of 0.1, I don't know what it is. I know that the sine of 0 is 0. So in this 0.1 is close to 0. So let's understand that this answer is going to be close to 0, but let's get an actual approximation for it using a linear approximation. So what we need is we need the tangent line. So we need the tangent line. So we'll try to do this one without a picture. So we need the tangent line equation for f of x equals sine of x. That's our curve. We need that tangent line at the x value of 0 because we're looking to plug in a number close to 0, and the problem even mentions look as near 0 at 0. Okay, so to get the tangent line equation, we need the slope of the tangent line first. So m is going to be f prime of x, right? That's how you do the slope of the tangent line. F of x is the sine of x, so the derivative of that is the cosine of x. And so we want the slope at x equals 0, so maybe I'll just put a subscript of x equals 0 on there. And we need to evaluate this at 0, and the cosine of 0 is 1. So the slope of our tangent line is 1. Now, we need a point, because we need the slope and we need a point on the line. Now remember from our last example that the point on the line is the point that is on the curve and on the line. So we know we're looking at x equals 0. The y value on the line is the same as the y value on the curve, which is the sine of 0, because the curve outputs are calculated using the sine of x formula. And the sine of 0 is 0. So our point is x is 0 and y is 0. Now we can proceed to find the equation of this tangent line. So we know that we're going to have y minus the y coordinate of 0 equals the slope 1 times x minus the x coordinate of 0. And when we simplify that, we just get y equals x. Or, even better, we can say the linear approximation function equals x. So that's the linear approximation. That is the linear approximation of the sine function at x equals 0. Okay? So what can we do with that? Now what we want to do is use that to approximate the sine of 0.1. So what this tells us is that f of x can be approximated by the L of x function near x equals 0. And so the f of x function is the sine of x, and the L of x function is simple here, it's just x. So the sine of an angle x is approximately equal to that same angle x as long as that angle x is near 0. So if we want to find the sine of the angle 0.1 radians, make sure you're in radians here because these functions don't have any units. So the sine of 0.1 is literally approximately equal to 0.1 itself. So that is our approximation. So if I want to know the error, then I'll take 0.1, our calculated approximation, minus the actual value of the sine of 0.1 using a calculator in radians mode. So let me make sure I'm in radians mode. Okay, so I do 0.1 minus the sine of 0.1. And in this case, my error is 0.0001665833532. And those are all the digits that my calculator shows me. But you can see it's a pretty good approximation. So it's very interesting to take a curve and be able to approximate that curve with a simple line near any decent point on the graph. Okay, so those are linear approximations, a fun little application of the derivative.